Hi, welcome to worksheet 22, Indefinite Integrals. This corresponds to book section 4.4. Last sections we talk about the area under the curve and the integral, how we write it as an integral, and how integral is basically antiderivative. So we're going to kind of expand that on idea today. We'll further discuss property of integral. So antiderivative of f is denoted by, now we can use the fact that integral is the antiderivative, so I can just write it like this. And then notice that I'm not writing any number on the top and bottom. So when I write it like this, this basically is saying like this is antiderivative of f. So instead of saying antiderivative of f, I'm just going to use this integral notation because that happened to be antiderivative. So I'm going to use that. So this is called the indefinite. Indefinite means there's no upper limit and then there's a lower limit, right? It's the integral as a general function. The definite integral is what we talked about last section, has upper limit and the lower limit, right? Lower limit and then upper limit. So many cases there are numbers attached to it. So you could go from a to b, 1 to 5, or 1 to x. Indefinite, we're just writing it as a symbolic, like a general function. All right, let's look at the first one. So symbolically, again, integral of f of x is a function whose derivative is equal to f of x. If we look at the definite integral when we have a to b, basically when you calculate this out, you're going to get a number. It's a number with the various interpretations. So it could be area under the curve, and today we'll talk about one extra interpretation of how we can use the integral. And they're connected by this. Basically, it's the f of b minus f of a. This is second fundamental derivative calculus. So antiderivative calculated at b, antiderivative calculated at a. All right, so kind of reviewing the property of the integrals, kind of same as what we talked about last time with the definite integral. It kind of behaves the same way. So when you have two things added, basically I can do this. We have two things added. We can split the integral. When I have constant, then I can pull it outside of. So integral like this. When you have x to the nth power, again, to take the integral, you add a power by 1 and divide. So this will be 1 over n plus 1, x to the n plus 1 power plus c. Again, when you take the derivative of constant c, it becomes 0. So this is the most general answer for that. Integral of k dx, just the constant k, there's no x in it. So that's k times x plus c. Because again, when you take the derivative of kx, like 2x, you get 2 as an answer. So if you go integral of 2, then the answer will be 2x, right? Integral of sine, again, integral just means antiderivative. What do I have to take the derivative of to get the sine x as an answer? Negative cosine, right? Negative cosine x plus c. Integral of cosine x, again, what do I have to take the derivative to get cosine x as an answer? The answer is sine x. Sine x plus c. Same for secant square. What do I have to take the derivative to get the secant squared? That would be tangent x plus c. And then what do I have to take the derivative of that to get secant tangent? That's secant x plus c. And for cosecant, it's basically the negative, right? So negative cotangent. Again, because the derivative of cotangent is negative cosecant, so I have negative there, and then basically same thing for the next one, negative cosecant x plus c. So this is just purely coming from the derivative of the trig functions. All right, let's see. You notice that here, what we just talked about, there's f plus g, where we can do f separately, and then you can do integral of g separately. And if it's f minus g, we can kind of do the same thing. So this is very convenient because when you have some complicated expression inside as your integrand, you can basically split it, take the integral of each one separately, and then add or subtract the answer. You notice that, however, we didn't have f times g. It doesn't split like integral of f times integral of g. Because the product rule is when you do f times g prime, you get f prime times g plus f g prime, right? So it becomes more complicated. Same for f over g. There's no nice formula for integral of f over g. And there's no nice formula for integral of f times g. Later sections, we're going to talk more about how do you do then, like if you have something like this. There are a bunch of special cases we're going to study, so it's to come. Let's look at example 1. It says evaluate each integral. I have integral of this over that. Again, we just talked about it. Like if you have something over something, it's just going to be very difficult to integrate. So here, as of now, like I'm looking at this, it's going to be a hard question. So what I'm going to do is I'm going to try to make it into something of addition. So here what I'm going to do is, we know that a plus b over c is basically a over c plus b over c. So I'm going to split it like that. So it's going to be 4 over x to the 5th dx plus x squared over x to the 5th dx. So again, if I were to rewrite it, okay, the first one, there's 4 there is a constant, so I can pull it outside. X negative 5 dx plus the second one, I have x squared on the top, x5 on the bottom, so that's x3 on the bottom, so it's x to the negative 3 power dx. All right, so how do you find the integral? The first one is x to the negative 5. You add the power by 1, so it's x to the negative 4. Then you divide by that, right? So it's x negative 4, x to the negative 4, right? Plus, same thing, I'm looking at this. You increase the power by 1, so negative 3 plus 1 is negative 2, and you divide by that. So it's negative 2, x negative 2, plus c. Again, because we're talking about general antiderivative, it can be there has to be a constant. Let me simplify this so they cancel out. So it becomes negative x to the negative 4 power minus x negative 2 over 2, and then plus c. That's my answer. I want to make sure I will check my answer. So how do I check my answer? This is supposed to be antiderivative of that. So when I take the derivative of this, I'm supposed to get that. So check. You can kind of see how for antiderivatives sometimes it gets kind of complicated. So check. Oops. Let's check here. Negative x to the negative 4 minus x negative 2 over 2 prime. Again, like here, I should have written this out, but when you take the derivative of a constant, it becomes 0 anyway. So this becomes, so for derivative is negative times negative 4 x to the negative 5, right? So you pull down the exponent, and then you subtract the exponent by 1. So it becomes negative 4 to negative 5. Minus negative 2 x to the negative 3 power over 2, right? So it's negative 2 power, so you pull down the exponent and then decrease it by 1. So there's a lot of negatives. So negative, negative, positive 4x to the negative 5 plus 2 will cancel out. So x to the negative 3 power. So that's what I had here. 4x to the negative 5th power is basically this one. And then negative 3 power is basically this one. So that's that. So we're good. All right, and let's look at example, the second one with the sine and cosine. It's like, okay, again, I have something over something, so this is going to be complicated. But here, maybe I can rewrite this as sine theta over cosine theta times 1 over cosine theta d theta, like this. We know that sine over cosine is just tangent. So tangent theta times, and I know 1 over cosine is secant. And I think we just talked about it. Integral of tangent theta and secant theta is here secant tangent, right? So we know that the derivative of secant is secant tangent. So that means integral of secant tangent is just secant. I know it can be very confusing. So here then, okay, so that'd be just secant. See? Again, you can check the answer, take the derivative of secant, you get secant tangent, which is this, which is just written version of that. All right, I'm gonna have you try the next one, very similar to the one we just did. And then I'll have you pause and then try the next one, and then we'll meet back at the next page. All right, if you're done with the last one, the answer should be negative cosecant theta plus c. All right, let's look at the next one here. Now we're going to try to kind of look at the integral and then give them like a different interpretation. So we'll incorporate integral with position, velocity, acceleration function. So like just kind of review before we talked about, let's say s of t represents the position function, position of the object, or it can be a distance. Then so s represents the position or distance. Maybe I should say distance here too, or distance. When you take the derivative of the position or distance, then you get the velocity. So this is the velocity, or sometimes we're going to refer it as a speed. And then again, second derivative means, so you take the first derivative, you get the velocity. If you take the derivative of velocity, you get the acceleration, right? So this gives you acceleration. Right? So that's how it's related like this. So when you think about it, I can think of the velocity as the antiderivative of acceleration, right? And I can think of the position as the antiderivative of a velocity. So maybe I can write it something like, you take the derivative to get the next one, but here is the antiderivative, right? And then here to here is antiderivative. I'm being lazy, I'm not writing everything out. So starting from s, take the derivative to get the v, take another derivative to get a. So if you start from a, you take the antiderivative, which is the integral, then you get v. You take another antiderivative, which is the integral, then you get s, right? So maybe I can write the antiderivative, the integral sign here, integral sign here. So that's how related. So in other words, v is the rate of change of s. So rate of change, velocity is just an example of rate of change. And then a is the rate of change of v, right? So basically, we can apply the fundamental theorem of calculus to the rate of change of for the position function, right? So again, kind of same thing. When you integrate something, you basically get the antiderivative. So what's the antiderivative of the velocity function? It's basically the position function. So s of b minus s of a. So position function at b minus position function at a. This is the second fundamental theorem of calculus, right? All right. So total change in distance, right? You're looking at the distance. So distance at the end, distance at the beginning, right? From t is a to b is given by this integral, a to b. Oh, I forgot to write a and b. A here, b on the top, where the velocity v represents the velocity. Let's look at example 2. Here, there's a little twist to this though. There's a one part where things get a little bit tricky. So here, I want to look at the difference between total displacement. Let me highlight displacement here. And versus the total distance traveled, right? So they kind of sound the same, and sometimes they're the same thing, but there are times they are not exactly the same. So we'll look at the difference between these two. Suppose that you live 5 miles from work, right? So, and then you drove to work and then came back home today, right? So you went to work and then you worked there and they came back home. So the question is, did you travel at all today? So even though, so I made extra comment here, even though you came back to where you started, right? So you started home, you went to work, you came back home. So did you actually go anywhere? Because when you look at it now, like you're back at where you started, right? But you actually traveled, right? So the question is, did you travel at all today? Well, in some sense, yes. I mean, obviously you went somewhere, but on the other hand, like you came back to where you came from. So did you travel, even though you ended up at the same place, right? So it depends on what you mean by travel, right? Or did you go somewhere? What you mean by did you go somewhere? So here I have two different distinct ways to express things. So the total distance traveled today, so that will be, in this case, that'll be 10 miles, right? Because you went 5 miles to work, and then you 5 miles back home. So you actually, your odometer, if you look at the car, it went up by 10 miles. So for sure you traveled in that sense. But total displacement is basically 0 miles. Meaning like you went back to where you came from, so you really didn't move at the end per se in terms of a position, right? So you came back to where you started from, so you went back, but you came back, so you basically didn't move in terms of change in position, right? So depends on what the question is. The answer could be 10 miles, or else it could be 0, right? If you just started from work, home to work, then both answer will be 5, right? Because you went 5 miles. That's how much you traveled. Displacement is from home to distance. From home to work, you're 5 miles away from where you started from, right? So in that case, both would have been 5. But if you come back, then, well, it's 10 for total distance traveled, whereas it's 0 for displacement. Okay? So how do you represent that in terms of integral? So here, total displacement of an object is given by just the integral. So we talked about, how when you integrate the velocity, you get the difference in change in position. So where did you start versus where did you end up at? So that's change in position. That's called displacement. Total distance traveled of an object. You notice here there's absolute value. So here I'm going to maybe highlight absolute value. So not only you're looking at the velocity, but you're looking at the absolute value of velocity. So basically when you come back, you're still like going forward, right? You're not going backwards. So that's why I had to kind of put the absolute value sign so that it gives you the total distance traveled. So there are two different things. So we're going to kind of look at it this way. So for example, if I kind of look at it graphically, let's say you have a graph something like this, right? So you have a velocity. That means your velocity is positive, and then your velocity is negative. If you have a negative velocity, that's kind of like you're coming back. You're going backward, right? So if you look at in terms of integral, this gives you positive integral. But if you look at the second part, because it's below the graph, if you take the integral of this, you get the negative number. So this is like, we talk about like a negative distance, negative area. So this is the same thing. It's like a negative distance means you're going back, right? So if you're talking about displacement, so if I go from, let's say, A to B, like your displacement will be positive here, but then this part will give you negative displacement. So if I just integrate from A to B, that'll get you basically 0. But if you look at total distance traveled, means like, oh, this is the distance traveled, and this is also distance traveled. So basically, I'm making this part into positive. That's why there's an absolute value. So if you're just going forward all the time, then they're the same thing. But if you once you start going backward, am I going to count that as a negative, or am I going to count it as positive? If I'm counting that as positive, that means you're looking at total distance traveled. That's why there's the absolute value sign here. All right, let's look at example 3. So you're given a velocity function, t squared minus 2, t minus 8. T is from 1 to 6. Okay. Sketch the graph of v is when is the object going forward and when is going backward. So kind of like what we talk about, because we're doing the velocity. So if you're going backward, then my displacement is going to be negative. So I want to know where the displacement is actually negative. So here I have t squared minus 2t minus 8. If I factor that out, where do I get? T minus 4, t plus 2. So that's where the root is going to be. So my graph is going to look something like this. T is going from 1 to 6. So maybe use red. So 1 is somewhere here. And then 6 is somewhere here, right? So this is, again, velocity function. So from 1 to 4, you're going backward. And then 4 to 6, you're going forward. Because this is negative, so you're basically going backward. This is positive, so you're going forward. So where is it going forward? From t between 4 and 6. When it's going backward, t is between 1 and 4. Okay. They say find the total displacement from 1 to 6. So their displacement is easier to find. I just have to integrate it. That's it. dt 1 to 6. So that'd be 1/3 t cubed minus t squared minus 8t. Evaluate from 6, 1. So 1/3 6 cubed minus 6 squared minus 6 times 8 is this. Minus, now I'm going to plug in 1. So plug in 1 here, plug in 1 here, plug in 1 there. So I get 1/3 minus 1 minus 8. If you calculate it all out, you get negative 10 over 3. Okay. So here you ended up going backward more, so you ended up at negative 10 over 3, right? Backward, basically. So that's the total displacement. It says find the total distance traveled from 1 to 6. So that one, I have to split my, because to do that, I have to basically look at the absolute value, right? So what I'm going to do is I'm going to split where it's positive versus where it's negative. So here I'm going to do, because when for absolute value, when the function is negative, I have to take like a negative of that, right, to make it positive. So here, the very first question is when is my graph negative, basically. So from 1 to 4, v is negative, right? So this is what I'm going to do. 1 to 4. So I have to do negative t squared minus 2t minus 8. Because this portion, v is, this quantity is negative. So if I put negative in front of it, this quantity is going to be positive. Okay, so, and then second portion is 1 to 6, sorry, 4 to 6. Because here it goes from 1 to 4, now I'm going to from 4 to 6. 4 to 6, my function is positive, so I don't have to do anything. T squared minus 2t minus 8. So I want to make sure this, I get positive answer here, and then I get positive answer there. This is because now we're doing total distance traveled. So when you go even backward, I should count that as a positive distance, right? All right, so when you calculate it out, I calculated on the side. So there'll be 18 for the first term, and then 44 over 3 for the second one. So total 98 over 3. Was there a unit? Nope. So whatever unit. Meters per second. So it's meters. Meters. Same here, meters. Okay. I'm going to have you do example 4. And I think that's it for this worksheet.